Hello everyone, welcome to this lecture on sliding and moving mesh models in Fluent software. This lecture is part of the Advanced Turbomachinery course by LearnCAX. Before we begin this lecture, let us see the outline of this particular session. First we will have introduction to the concept of sliding mesh. Then we will see in detail the sliding mesh concept, how to set up a sliding or moving mesh problem, and in the end we will see the solution strategy and post-processing tips for using sliding mesh model. First, an introduction. The sliding mesh model allows you to set up a problem in which separate zones move relative to each other. The motion can be translational or rotational. The relative motion of stationary and moving components will give rise to transient interaction. Often, the transient solution that is sought in a sliding mesh simulation is time periodic, which means the solution repeats with a period related to the seed of the moving domain. After that, there is a generalized case of the dynamic mesh model, which allows you to move the boundaries of the cell zone relative to other boundaries of the zone and to adjust the mesh accordingly. The boundaries can move rigidly with respect to each other and deform as well. Then how to choose between the sliding mesh and the dynamic mesh model? Many problems can be solved by both. If there is no mesh deformation, then we use the sliding mesh approach. If mesh is deforming or if the mesh motion is a function of the solution, then we use the dynamic mesh approach. When we require to see time varying results rather than time average results for rotor-stator interaction, sliding mesh comes into picture. Sliding mesh model can compute the unsteady flow field. It is the most accurate method for simulating flows in multiple moving reference frame, but it is also most computationally demanding. In situations when there is no interaction between stationary and moving parts, like when there is only a rotor, then it is not necessary to use sliding mesh. You can go with the moving reference frame models. If you want to approximate the unsteady flow with a steady representation, then you can go with the multiple moving reference frame model. You should use the sliding mesh approach only when you are interested in capturing time varying phenomenon. To use the sliding mesh technique, we need two or more moving cell zones. If we generate the mesh in each zone independently, we can merge the mesh files prior to starting the calculations. Each cell zone is bounded by at least one interface zone when it meets the opposing cell zone. The interface zone of the adjacent cell zone are associated with one another to form a mesh interface. The two cell zones will move relative to each other along the mesh interface. During the operation of the sliding mesh calculations, the cell zones slide relative to one another along the mesh interface in discrete steps. The left figure shows the initial position of the two meshes, and their position after some translation has occurred is shown in the right figure. All non-conformal interfaces are automatically updated by Fluent during the calculations. There is no requirement of node alignment. What type of shapes can the mesh interfaces have? The mesh interfaces and associated interface zones can be of any shape. The two interface boundaries should be based on the same geometry. The left figure here shows an example with linear mesh interfaces, and the right figure shows a circular arc mesh interface. So this is a linear interface and this is a circular arc interface. The dynamic mesh model in Fluent can be used to model flows where the shape of the domain is changing with time due to motion on the domain boundaries. The update of the volume mesh is handled automatically by ANSYS Fluent at each time step based on the new positions of the boundaries. To use the dynamic mesh model, you need to provide a starting volume mesh and the description of the motion of any moving zones in the model. This motion can be prescribed using either boundary profiles, user-defined functions, or the 6 degrees of freedom solver. The description of the motion is to be specified on either face or cell zones. If the model contains moving and non-moving regions, you need to identify these regions by grouping them into their respective face or cell zones in the starting volume mesh that you generate. Regions that are deforming due to motion on their adjacent regions must also be grouped into separate zones in the starting volume mesh. The boundary between various regions need not be conformal. You can use the non-conformal or sliding interface capability to connect various zones in the final model. Let us see the conservation equations used to model dynamic mesh. The integral form of the conservation equation for the general scalar phi on an arbitrary control volume V whose boundary is moving is written as shown here. So this is the conservation equation used to model the dynamic mesh. Here Ug is the mesh velocity of the moving mesh and dabba V is used to represent the boundary of the control volume V. Using the first order backward difference formula, the new volume at n+1th level is obtained using time step delta t. So this is the new volume by which the volume mesh is updated. Let us now see the theory for the sliding mesh approach. Now let us see on what equations the sliding mesh model works. The sliding mesh model is a special case of the general dynamic mesh model where the nodes move rigidly in given dynamic mesh zone. Also, multiple cells zone are connected with each other through non-conformal interfaces. As the mesh motion is updated in time, the non-conformal interfaces are likewise updated to reflect the new position of each zone. In general, conservation equation formulation, which we saw in the earlier slide of the dynamic mesh, is also applicable or used for the sliding mesh. Since the mesh motion in the sliding mesh formulation is rigid, all cells retain their original shape and volume. Hence, the time rate of change of cell volume term becomes 0, and the equation reduces to something shown here. Whereas the new volume is also equal to the old volume. The solutions for the sliding mesh model are inherently unsteady as they are for the dynamic mesh model. Now, after we have seen the theory and basic concepts of the dynamic mesh model and the sliding mesh model, let us look at the constraints of the sliding and the dynamic mesh models. The mesh must have a different cell zone for each portion of the domain that is sliding at different speed. The mesh interface must be situated such that there is no motion normal to it. The mesh interface can be of any shape provided that the two interface boundaries are based on the same geometry. If there are sharp features in the mesh, it is important that both sides of the interface closely follow these features. If you create a single mesh with multiple cell zones, you must be sure that each cell zone has a distinct phase zone on the sliding boundary. The phase zone of two adjacent cell zones will have the same position and shape, but one will correspond to one cell zone and one to the other. If you are modeling a rotor stator geometry using periodicity, the periodic angle of the mesh around the rotor blades must be same as that of the mesh around the stationary vanes. All periodic zones must be correctly oriented before you create the mesh interface. The edge of the second interface zone must be offset from the corresponding edges of the first interface zone by a uniform amount. Some portion of the two interface zone must overlap. The non-overlapping portions of the interface zone must have identical shapes and dimensions at all times during the mesh motion. One pair of the conformal periodic zones must be adjacent to each of the interface zones. You must not have a single sliding interface where part of the interface is made up of a coupled two-sided wall while other part is not coupled. In such cases, you must break the interface into two interfaces, one that is coupled interface and the other is standard fluid interface.